Hello, marvelous AP Calculus students, and welcome back to our second to last lesson in our first topic of AP Calculus AB. Our second to last lesson is actually our second theorem for the entire year. Now, there kind of are one or two other theorems, but we don't really call them as such. These are kind of the 5 ones that you're asked to use to justify various free response questions. So the title of our lesson is the Intermediate Value Theorem. And it goes straight towards learning goal number 4, which is applying the squeeze theorem and the intermediate value theorem. We're going to start with actually a quick Desmos activity. And you're not actually expected to know what the intermediate value theorem is yet, but this activity is kind of cool because you're going to discover what the intermediate value theorem is. So even though I'm not there today, I'm going to expect you guys to be able to figure out, or maybe even to yell out or shout out with enthusiasm the answers to each of these. So we're going to quickly look at roots of functions. And you guys see roots, you study them a lot in Algebra 2. Sometimes you hear roots called zeros or x-intercepts, right? But for our purposes, a root is where a graph crosses the x-axis. Okay? Crosses or touches, it could bounce off there. So let's begin. Where must there be roots? So we have a purple graph over here, and it's representing a continuous function f of x. And parts of the graph are hidden behind those black circles, a, b, and c. So the question is, behind which circles must f of x have roots? Okay, so look at those 3 and then think about it. And if you're excited, you can call them out. Is it A? Is it B? Is it C? Now, notice it says must. Right? So which one must they have roots? And I think most of my classes usually just say B is the only one for must, right? We'll talk more about these next. And you said B was covering a root. How do you know? Right? How would you justify that to somebody? How do you know there has to be a root there? And you'll probably have a couple different answers, right? The graph starts above the x-axis and it ends up below the x-axis, something like that. The y values are positive, the y values are negative, or you're like, clearly it has to cross over the x-axis. Look at the graph. All right. Now, where could there not be roots for sure? Sometimes there's a little discussion on this. You're like, oh, maybe A, definitely C, right? There's definitely no roots on C. For A, could there definitely be not roots? And the answer to that one is, I'm not sure, right? It could dip way down below A and then go back up, or maybe it just does like a little travel above the top of A. Okay, he said C must not be covering a root. Well, think about the y values, right? Below we have, oops, I'm trying to get on the graph there. There we go. Below C we have like 0.8 for a y value. Above C we have like 3.2. I think there's probably no 0 y value in there, right? Okay, now behind which circles might f of x have roots? Now we get the game, right? Okay, A could have a root. All right, we know that. So let's go ahead and check our predictions. Let's try B first. Hey, you're right, B had a root. Woo, C did not have a root. And A did not have a root either, but it could have. All right, so now that we get the game, let's try again. So here's our function, red graph, continuous function g of x, parts are hidden. Which ones must have roots? A, B, C. Now, I imagine having done this activity several years in a row, most of you will say none of these. Okay. Then our next one, might it have roots? Ooh, now that's an interesting one. Could A potentially have a root? Could the red graph drop down and bounce off the x-axis and come back up? Maybe, but it kind of looks like if you're looking at A down there, I don't see any dots. So I'm going to say maybe A might have roots, but I think B and C could definitely have roots, right? The red graph could drop down and come back up for both of those. Is it impossible? I'm going to go with A, but that is absolutely debatable. Okay, let's check. C. Oh, C had 2 roots. B had none, and A had none. All right, so tricky. All right, let's try again. The orange graph, continuous function h of x, same idea, behind which must it have roots? Okay, well on A we notice that there are y values positive here, but I can't see the bottom of the graph on the left side. B, I'm not sure. Ooh, but look at C, right? C, we have some positive y values and then some negative y values. So I think in order to go from positive to negative, we'd have to cross over 0. So I think C probably has a root. Okay. Might there have roots? I think A and B both could have roots. Can you visualize that? And must not be roots? I don't know. I'd say none of these. So let's check. C was the one I was confident on. There's a root. Good. B, there's no root. Okay, but A, there was a root. Okay, now we didn't know that one for sure. We knew C for sure. We weren't sure about A. Okay, last time. Blue graph, function, j of x. Let's go ahead and check this one. Behind which circles must j of x have roots? As we look at this one, must have maybe, I think C almost certainly, right? Because we're negative y values than positive, so C has to have them. Okay, and then we say, where might there be roots? B could bounce up, then come back down, and A, I think A and B both could have some. And it is impossible, I'd say none of these. Okay, now we get the game, we've done really well, so we're on A, obviously not, B, no, and then C, oh. C, there were no roots here. What changed? Yeah, did you notice, right? If you go back, the blue graph represents as a function j of x. But on the other ones, the orange graph represents a continuous function h of x. Did you notice that they left off continuous? I think some of you probably did, but most of you may have been lulled into complacency by old Mr. Grant there. So, jumping back through, how can you know where there are roots? Well, I think one thing that needs to happen is, if we look down at this purple graph, right, our kind of right above B here, right above B, we had positive y values, and below B, we had negative y values. So I think on one side of the kind of giant circle there, we had positives. On the other side, we had negatives. And what else had to happen based on the end? And of course, the other thing that had to happen was our function had to be continuous. Otherwise, we just didn't know. There was too much uncertainty. And so with that, we're done with the lesson for today. You know the IVT. Or maybe we should do a little bit more. So here we go. We learn 5 total theorems that need to be really applied on free response questions. And we already know one of them, which of course is the squeeze theorem. Okay. Do you guys remember what needs to be true to apply the squeeze theorem? Right, I think there are 2 things, weren't there? Right, for the squeeze theorem, we needed 3 functions. We needed a function to be in the middle. Right, so if g of x is in the middle, then the guarantee, or what happens when you apply the squeeze theorem, is that we are able to find the limit as x approaches a of g of x. But the other thing we need is that we need the limit as x approaches a of f of x, the bottom function, to be equal to the limit as x approaches a of h of x. And if those 2 things happen, then we're able to find this limit, and it's equal to those other 2. Okay? Now, let's go ahead and take a look at the intermediate value theorem. And let's make sure we can identify the criteria that have to happen and what that guarantees. Okay, so the IVT, suppose that f is continuous on the closed interval a to b. Remember, we talked about that closed interval last class. It's nothing we have to prove. It just means you draw a continuous line or curve from endpoint to endpoint. And let n be any number between f of a and f of b. Then there exists a number c on the open interval a to b such that f of c equals n. Oof, okay, there is a lot to that. So let's try and break it down. First, let's see if we can identify the criteria for use. What has to happen? And let's make sure we understand what those criteria mean. So the first one is that f is continuous on the open interval a to b. So let's look at maybe our 2 example problems and see if at least the first criterion is met. So the first one says, explain why f of x equals x cubed plus 3x minus 2 has a 0 on the closed interval. Well, if we look at f of x equals x cubed plus 3x minus 2, is that function continuous on the given closed interval? Well, the answer here is yes, because this is a cubic function, right? Cubic functions are always continuous. It doesn't matter what it looks like. And because it's continuous on a closed interval, we don't have to prove that. The AP exam assumes that that is an Algebra 1 or Algebra 2 skill. They need you to know that or assume that you know that. So in our answer down below, there's going to be a little bit more to show. We're going to say something like, as f of x is continuous on 0 to 1. Okay. Now you don't have to prove why, and we don't want to say if f of x is continuous, because then it sounds like you don't know. Just tell them it's continuous. Okay. And let's look at b. Explain why g of x equals x squared minus x minus cosine of x has a 0. Now that's a function that might give you pause, because I bet you don't know what that looks like. But, and we're going to expand on this more next class, it turns out that if you have a function that's made up of adding or subtracting continuous functions, then that function itself is continuous. So we look at the individual parts. Is x squared continuous? Yeah, it's a parabola. Is x continuous? Yeah, it's a line. Is cosine of x continuous? Yeah, it's a cute little wave, right? And so if you put all those together, then our new function g of x is continuous. And here's the cool part, you don't have to prove it. So for this one, as g of x is continuous on 0 to pi. Some people will say, well, wait, is CONT an abbreviation for continuous? Maybe, I don't know. But if you're reading this, do you know what CONT means in the context of this problem? Sure, and so you would earn credit for it, right? I don't think there's an official abbreviation for continuous, but if the reader knows what you mean, you're fine. And we would all know that CONT is continuous. Okay, so that's the first criteria for use, and we've checked that off. Then we have the second part, and this one is pretty tricky, especially without a graph. It says let n be any number between f of a and f of b. And let's break those down. If we find f of a is going to be a y value, right? And so is f of b. That's another y value, right? F of something means substitute something into the function. Now, where are these a and b's coming from? Let's see, a and b. Oh, a and b, those are the endpoints of our interval. So I think for part of this, we should probably find f of a and f of b right away. And that is, in fact, probably the first thing I'd suggest on the intermediate value theorem. So let's go ahead and find f of 0, okay, and f of 1. And we'll do the same thing over here. We're going to find g of 0 and g of pi. Okay, so take a quick second. I'll put the work up there as well. You should be able to do this without a calculator. And in fact, both these are no calculator, but you will need a calculator for today. So be ready with that calculator. So if you finish early, grab one. If you already have one, great job, but let's do this without a calculator. Okay, so I'm seeing -2 for the top, right? That means I made the point 0, -2. And I guess I should zoom in. If I substitute in 1 plus 3 is 4, minus 2 is 2. And so I believe that makes the point 1, 2. Not too bad. Let's try the other side. G of 0, well, that's 0 squared. And you don't have to write this intermediate step where I'm showing that I'm substituting in 0. But for your notes, maybe it's not a bad thing. 0 minus 0 is 0. Cosine of 0, 1. Good. I can all hear you guys yelling that. That was exciting. But there's a negative, so that's -1. So I'm seeing 0, -1. And then g of pi. So we have pi squared minus pi minus cosine of pi. Now here things get a little murky because I'm not quite sure about this. Pi squared, right, is approximately, maybe I'll use an approximate right here, is approximately, let's see, pi 3.1, let's call it 3. 3 squared is 9. Pi is approximately 3. And cosine of pi, we know, of course, is -1. So I'm seeing 9 minus 3 is 6. 6 plus 1 is approximately 7. Now we're going to do a little bit more with this. We'll come back to this in a second. But let's just say it's in the ballpark of 7. Maybe it's 6, maybe it's 7, maybe it's 8. Somewhere around there. It doesn't have to be that perfect. So we found the y values of the endpoints, right? So we found, and maybe I should do a different circle. We found these y values here. Okay. Now they said, let n be any number between those y values. So for a, negative 2 to 2, what are some numbers between those? Well, negative 1, 0, 1, 1.5, right? And between this one, between negative 1 and 7, well, negative 0.5, 0, 1, 2, 3, 3.1, pi is there, e is there, lots of numbers between. Let n be any number between them. Those are the two criteria. We state that the function is continuous, and we find the endpoints. So then we have, there exists a number c from a to b such that f of c equals n, and that's really vague, right? We have c, which is of course an x value, and they're saying that we're substituting this x value into the function to get an n value. And you're like, c and n, neither of those are numbers. What's happening here? So let's look at a specific example. A, I think. Explain why f of x has a 0 on this interval. Now that's actually a little bit more complicated. So let's examine the idea of a 0. A 0 we just talked about is like a root. That's an x, not an x value, an x-intercept. And an x-intercept always has the form some x value comma 0. Right? Think about that. That'll move you along the x-axis. So when they say explain why this has a 0, what they're saying is the n in this case is 0. They're saying let n be any number between the y values. So the n is a y value. And they're saying, does there have to be this specific y value on the interval from 0 to 1, on the interval from a to b? Well, if you think about this, right, we have a y value of negative 2 and a y value of positive 2. And they're asking us, does there have to be a y value of 0 somewhere in there? Now, visually, and we aren't going to do this every time, but I think visually this is nice to do at the beginning, right? I'm just going to sketch a really quick graph of what we found. So we have the point 0, negative 2, and 1, comma 2, and I think we can probably do something like this. Here's the point 0, negative 2, and here's the point 1, comma 2. Now this is all part of a cubic function, which we said is continuous. So at some point, I don't know what this looks like, and it doesn't matter. Let's say it's cubic over here. At some point, I'm going to get here, and then at some point, I have to get up to the other point. Agreed? Right? Maybe it is a little bit different than that. Maybe it kind of curls like this, but at some point, I have to get up there, and I'm just erasing like half my graph. And I certainly can't do this because then it's not a function. Right? So from here to here, think about the path of my curve. I come up here, maybe now I'm at a y value of negative 1. Come up here, now I'm at a y value of 0. Come up here, now I'm at a y value of 1. Come up here, now I'm at a y value of 2. In fact, what we're saying is if you start at a y value of negative 2 and you end at a y value of positive 2, do I have to cross through all the other y values between those on the way from the beginning to the end? I certainly do. And this question is saying that does there have to be a y value of 0, right? A y value of 0. And visually, without even a graph, we can see that. We started at negative 2. We ended at positive 2. And what this intermediate value theorem is saying is that n is any number between the endpoints. So this question could have said, explain why f of x has a y value of 1 on the interval. And there had to be a y value of 1 because 1 is between negative 2 and 2. This one, though, just said, explain why there's a y value of 0. And we've already shown everything we need for it to happen. We found the values of the endpoints, zeros between those. We've said that f of x is continuous, so let's finish with our conclusion here. So as f of x is continuous, and here's how this is usually presented. We put the smallest value first, and the smallest value I'm going to say is f of 0, right? That's small. So I'm going to say f of 0 is less than, what y value are they asking us to find? They're asking us to find a y value of 0. And that in turn is less than the big y value, f of 1, which was 2. So what we're saying here is that 0 is in between the endpoints. One endpoint is smaller, one endpoint is larger. So as f is continuous on the closed interval, and 0 is between the endpoints, somewhere between, in this case it's exactly in between, then the IVT, Intermediate Value Theorem, right, explains, or guarantees, we'll spell that one later on, why f of x has a 0 on 0 to 1. And now notice when I wrote this conclusion here, the IVT explains, and then this part right here, I literally just rewrote plus minus a word or two what was in the problem. Sometimes students worry about, oh, did I write this correctly? I'm not sure one way or another. The problem wrote it correctly. Just rewrite what the problem asks. Explain why. This is why. So there are three things we had to discuss here. We had to talk about continuity on a closed interval. We had to show that the y value we wanted was between the endpoints, and then write a quick conclusion that answers the question. So at this point in time, I'd like you guys to try two things. I'd like you to try B, very similar to A, and then I'd like you to use your calculator to actually find the 0. And there's a specific way you can do that on your calculator. Now, you may not have enough time in class to pause this video. If you do, pause it, but if you don't, you can just keep on listening, right? So on B, they said explain why f of x has a 0. So it's very similar to the other one. Now, if you're looking at this, we're like, okay, is 0 in between g of 0, which is -1, and g of pi, which is approximately 7? Is 0 in between those two? Yeah, I think so. Now, we need to be careful here, because honestly, this part at the end I would not write on the actual AP exam. Instead, I would just say that pi squared minus pi minus cosine of pi, it doesn't have to be 7, right? This answer, if the first y value is -1, what type of value does this have to be in order for there to be a 0 on this interval? Well, this value just needs to be any positive number. And just by our approximations up here, are you pretty convinced that this is a positive number? Maybe around 7, maybe 6, maybe 8, maybe my rounding was really bad, maybe it's 5, but it's definitely positive, isn't it? And so what I would do instead of doing this is I would just say all of this is greater than 0. That's very safe. We don't have to deal with these weird approximations. So I'm just going to say greater than 0. And then our conclusion is pretty much the same. As g of x, make sure you use g, not f, this function is called g, is continuous on 0 to pi. And let's use our endpoints. G of 0 is the smaller endpoint. That's less than the 0 they asked us to find, which in turn is less than g of pi. Then the IVT, we can try for guarantee this time. Guarantees, right? Say it like that and you'll get it right. Guarantees that g of x, and watch, this is the part where I'm just going to write the rest of this right here, okay? That g of x has a 0 on 0 to pi. So again, continuous on a closed interval, endpoints that are kind of sandwiching the value in the middle, and in fact, intermediate. What does intermediate mean? Well, think about a game, right? We have maybe skill settings on a game. You have beginning, intermediate, and hard, right? Intermediate just literally means in the middle. So the intermediate value theorem is you're trying to show that this value is intermediate to the values on either side. It is in between them. Okay, with that being said, why don't you go ahead and use your calculator to find the 0 that we're talking about for each of these? Because notice, we didn't actually really do much math besides plugging in a number. It didn't say find the 0. In fact, finding the 0 is very challenging. If you were to set 0 equal to x cubed plus 3x minus 2, and I said solve that, you'd probably be stumped. That's not factorable. That's not a square. You can't solve for x. You'd have too many x's here. It's really challenging. But luckily, we're armed with a graphing calculator. And because it's a graphing calculator, you should probably graph both of those functions. Now, I've already graphed both of them, and I'm going to show you how to do them once on the Inspire and once on the 84, and I'll just show you one of each, right? So if we do this, I've got one here and one here, and hopefully it saved all my functions. I think it did, though. That would be very kind of it. Let's see. It's going to drag this guy in here. There we go, something like that. And now I can see both calculators-ish, and that's giving you enough time to get everything graphed, too. Okay, so let's rock and roll. So on my 84, I actually have a bunch of functions plugged in here, and that's because I tried to front load all the functions we need. I have the equal sign turned on for the top function, so I'm going to go ahead and graph that. If yours doesn't show this way, remember the first thing you should always do when you turn on your graphing calculator is zoom standard, right? Zoom and then 6 on the 84, zoom standard so that it sets the window for you. On the Inspire, I have the first one on. I'm going to hit Tab to go back up to my graphing screen. It jumped right to 9 because I have all these in here. I'm going to go ahead and turn this one off, though, and I'll turn on the second one. Uh-oh, that's not great. It really did not like my pen there. That's awkward. So again, maybe you guys are taking some time to go through and get these graphed. I don't want the fifth one to graph. Thank you. I do, however, want the second one to graph. Good. Okay, so I've got these two. I'll hit enter there. Nope. Enter and click. There we go. Now, I'm going to go ahead and find the 0. On the 84, to find the 0 of a graph, we actually don't want to do trace. Trace can sometimes give us some false positives. Instead, we want to use the calculate function that's above trace. And to access that blue menu here, we need second. So I'm going to do second, calc, and then we're trying to find the 0. So let's do 0. Okay. Now, you'll notice here that we can go right, and that moves the x values to the right, and the y values are getting larger, and left moves the x values to the left. They're asking for a left bound. So we're saying, I think this right here is the 0. But they want you to go to the left of that. It doesn't matter how far left. I'll just go a little bit left, and I'm going to hit enter. You'll notice when I do that I've got a little triangle up above, and depending on the 84 version of your calculator, it might be a triangle, it might draw a line, doesn't matter, but now it says right bound. So I'm going to take this back to the 0, and I'm going to go to the right of the 0, somewhere over here, and hit enter. Okay, we have another triangle here, and now we've got a region from the left and the right. And we need to make sure that the 0 is between that region, because what your calculator is going to do is it's just going to start plugging in x values from the beginning to the end of the region into your equation. And as it gets close to 0, it plugs in closer and closer x values until it has a good approximation. So it says, should we guess at where the 0 is? And you're going to hit enter a third time. You have to enter 3 times on the 84. And when you do that, it says the 0 is 0.596. Okay, so to answer the question from earlier, so 0.596, remember that, as I go back here, it says explain why there's a 0 from an x of 0 to an x of 1. Is 0.596 between 0 and 1? Yeah. If you were to substitute 0.596 here, you would get 0, approximately. But we didn't have to do that. We just had to prove that there was a 0. We didn't do hard math. We just plugged in the endpoints. Okay, to do this on the 84, I'll just keep both these up here because why not? To do this on the 84, the Inspire, everything on the Inspire is in menu. So I'm just going to hit menu right here, and then we're going to go to Analyze Graph, which is 6. The top option, 1 is 0. Now once you're here, I would really suggest you just lightly run your finger over the trackpad up at the top so that you can move this dashed line from left to right. You can also click the left and the right, but it's really just a lot easier just to move it from left to right. Now you'll need to be careful with this guy, and you should try it on the 84 too. I don't want to click all the way over here and then go to the upper bound, which is somewhere on the left over here, because it only finds 1 0. It says nothing there, right? But either way, we really want to make sure that we do our first 0 somewhere in between, like here, and then drag to the right to get to the actual 0 we cared about, which is 1.25-ish. Now, by the way, the 84 also hides extra decimals. It says you wanted me to round, right? And if you don't want it to round, then what you do is you actually hit the plus button over here, and the plus button will show more zeros. That's really important because the 84 shows at least 3 decimals, 3 digits past the decimal, which is required by the AP exam. If you were to write 1.25, you wouldn't get full credit. You need the extra 1. Now, if you own your Inspire, you can always change the settings to show more than 2 zeros, but that's a good habit to get into if you find a 0. Make sure you hit that plus, right? To do fewer, you can just hit the minus. All right, so we have an idea of how to find zeros there. Nothing terrible. Now let's see what else we're actually doing today. Okay? You can actually use your calculator to find the 0 of an equation and use that to solve any equation ever. And that's super powerful, right? If we look down below, it says, solve this equation using your calculator's 0 tool. Well, this is a pretty tough equation to maybe solve. I mean, you could multiply this over and maybe it would solve nicely, maybe not. But what we could do is we could just slide the 6 over. When I say slide the 6 over, of course, I mean subtract 6 from both sides. And so that would look like this, equals 0. Right? And if you do that, we could actually graph this equation. We could graph y equals this, ignore the 0, and we could find where does this graph equal 0. And by doing that, we'll have solved the equation. Now, I don't know if I was on top of it enough to have that ready, but maybe I can switch it on Desmos really quickly. I was. Okay, cool. So I slid the 6 over there, right? So if I look on Desmos really quickly, Desmos does this pretty well. It's nicer because you can just click the zeros on here. But yeah, on here we can see that there are 2 zeros, 2 and 3 in this case. So if I jump back to this problem, right, to solve this problem, we just graphed the equation, found the zeros, and this tells me that the answers are 2 and 3. And if this was a calculator active question on the AP exam, that's what they'd expect you to do, at least one method. They give you a problem, they'd expect you to be able to solve that. Maybe not algebraically, you would just show the setup and then go straight to the answer. In the intermediate step, pun intended for this lesson, is you would be graphing this equation and finding where it's equal to 0, right? You use that 0 trace again, but either way, that's a pretty clever way to solve any equation. But let's go ahead and try a couple more. It's pretty important to note that the theorem questions typically don't ask you to find the value, but just they want to know if the value is guaranteed. So let's not do too much work below. Right, we have 2 different equations here, and if again you have enough time, pause me and try those and then unpause it. But if you don't, you can keep on listening to my soothing voice. So must there be a value c such that h of c equals 6 on this interval? Okay, well, let's think about this. Okay, the first thing we want to do is we probably want to find the values of the endpoints. That's what we did before, right? We found h of 5 halves, and then we're also going to have to find h of 4. Now, h of 5 halves without a calculator seems pretty obnoxious, but I think we can do it, right? We just substitute 5 halves in for all the x's, and let's see what we end up with. 5 halves squared, that's going to be 25 fourths. And then we have to add 5 halves to that, so let's make that over 4 as well by multiplying 2 over 2, right? That's 10 fourths. And then for the denominator, let's see, we're 5 halves minus 1 over 1. Let's make this into a fraction. That's going to be 5 halves minus 2 over 2. So I'm looking at 35 quarters divided by 3 halves. Shouldn't have done h of 4 yet. Awkward. H of 5 halves then, let's do that algebra 2 trick and multiply by our reciprocal. It's kind of like a version of skip flip multiply, right? And we end up, let's see, before I divide those, we can cross reduce to get here. I'm looking at 35 sixths. Okay, that one's pretty good. Now let's try h of 4 and pray that that one looks a little nicer. Oh my gosh, who made up this problem? It was me. So let's see, we have 4 squared plus 4 divided by 4 minus 1. This one looks way better, right? 16 plus 4 is 20. This is 20 thirds. Okay. Now, what are they actually asking us? They're saying, is there some x value where when you substitute the x value in, the y value is 6? Well, let's take a look at our y values. We have 2 of them, don't we? We have a y value of 35 sixths, and we have a y value of 20 thirds. But they're asking us, essentially, is 6 between those two y values? I don't know. We probably need them as decimals, don't we? But I think decimals for this aren't too bad, right? Let's think about 6 into 35. How many times does 6 go into 35? Well, it's not 6 times, because 6 times 6 is 36. So it's 5 and some change, right? 5 and something. The more astute of you might see that this is 1/6 short of it, so it's actually 5 and 5/6, but just 5 and something is fine. And then 20/3, let's see how many times 3 goes into 20. Well, 3 times 6 is 18, 3 times 7 is 21, so 6 is just a little too small, 7 is too big, so I'm going to say that that's 6, and it's actually 2/3 short, but that doesn't matter. 5 and a bit, 6 and a bit is 6 in between those two values? And the answer is yeah, it is. So let's write our conclusion. First step of the conclusion, as h of x is continuous on 5/2 to 4. Oh, wait a second. Let's go back to this equation. I don't think that function is continuous, is it? If you look at that, do you see any possible discontinuities there? I think if x is, I think there probably may even be a vertical asymptote there. I think if x is 1, 1 minus 1 is 0. You'd be dividing by 0. It's not continuous at an x of 1. So I guess we can just stop there, right? But wait. It's not saying h of x is continuous everywhere. It's saying h of x is continuous from 5/2 to 4. 5/2, let's see, 2 into 5 twice and 1 left over. That's 2.5. Is h continuous for all the x values from 2.5 to 4? Yeah, I think it only breaks at an x value of 1. So remember, it just has to be continuous on this interval, and it is. So as h of x is continuous, and let's take our endpoints. Okay, which one's the smaller endpoint? H of 5/2 is. So h of 5/2 is less than the 6 that they asked about, which in turn is less than h of 4. Then the IVT guarantees, and I'm going to be lazy here because I'm kind of running out of time and I just don't feel like writing it, but you probably should. I'm just going to put a star kind of up here, right? A value c such that h of c equals 6 for all this on this interval. And that's it. Okay. Let's try the last one. Does the IVT guarantee that k of c equals 2 for this equation on the interval 0 to 2? Well, as you go through and try this, right, let's find our endpoints. So we'd find k of 0 and k of 2. K of 0, 1 over 0 minus 1 plus 2. Negative 1 plus 2 is 1. And k of 2, 1 over 2 minus 1 plus 2. That's 1 over 1, which is 1 plus 2, which is 3. The question we ask, is 2 somewhere in between our y values? Yeah, it's in between 1 and 3, so that's looking pretty good. And then we do our conclusion, right? As k of x is continuous on 0 to 2, and so on and so forth. But did you notice anything? Is k of x continuous on that closed interval? What would break this function? An x of 1 would break this function, right? Oh, and so h of x isn't continuous. Uh-oh. And if that's the case, then the right way to end this, and they wouldn't actually ask you this on a free response, it might be more of a multiple choice question, is we can't draw a conclusion using the IVT. Because here's the thing. K of 0 being 1, K of 2 being 3, there could certainly still be a y value of 2 between those two endpoints. We just can't use the IVT to do it. And if we can't do that, is there maybe another way? Well, I'll show you right now. Instead of using the 0 tool, let's go ahead and use the intersection tool. The intersection tool is a great one, and honestly, I use it almost as much as I use the zero tool. I like it because instead of having to move the 6 over to the other side, instead we can just take this one giant equation and treat it as two separate problems, right? In Algebra 1, we learned that we can write a system of equations with each side of an equal sign. Now, you might not remember that from Algebra 1, but you did learn it. I promise. I taught it. Okay, there's one, and here is, we'll do this color, here is the other. We can break this into a more complicated looking system of equations because through substitution, we could of course substitute this in for y, and you'd be back where you started. But the reason I'm doing that is because a different way to solve a system of equations besides using algebra is to graph each equation and determine where the graphs do what. Well, it's of course where they intersect. So what I'm going to do is I'll pull up both calculators and I'll solve each one with the calculator one time. So let's see, let's pull this guy up and this one. Okay. On the 84, I'm going to have to go back through and I'm going to turn off my equal sign here. I'm just going to go down and take two functions. I'm going to need x squared plus x over x minus 1 and 6. And while you're getting that one set up on your 84, on the Inspire, I'm going to hit the Tab button, get back up here. Whoa, buddy, it's okay. And I'm going to turn off the function I just worked with, which was this one, and drop down. Nope. Stop that right now. The Inspire really does not like my touchscreen. And I'm going to turn on this guy, and nope, stop that. And maybe it'll let me go back, maybe it won't. Who knows? And the other function, which was 2. Great. And click down there. Okay, so let's do the 84 first. So I'm going to hit enter. Nope. I'm going to hit graph. I promise I know how to use these. We've got that and that. Okay, now looking at these two, I see a green function, which is my line, and the pink function, which is my 1 over whatever, floating up here, or x squared plus x over x minus 1. And it looks like the green function intersects, but I think what I'm going to do is I'm going to zoom my graph in just to make sure. And I'm going to use my absolute favorite zoom. I'm going to use zoom box. So zoom and then 1. Okay, and so I'm going to jump up here, holding the up button to move this guy up very, very slowly, apparently. That's exciting. And as soon as I get pretty close to that area, this is just like watching paint dry. I'm going to go ahead and hit kind of on this upper left corner, and you'll see what I mean by left corner. I'm going to hit enter. As soon as you hit enter, yeah, I know. As soon as you hit enter, it's going to let you start to draw a box. So I'm going to hit enter once and then go down. And as you go down, then it's going to give you a line. And you're like, that's not a box. But then I'm going to hit right. And when I do that, it's going to make this beautiful rectangular box here. And what I'm doing is I'm just telling it to only zoom in on that specific spot. And I'm going to hit enter that third time. When you do that, we can see that these cross in 2 spots. Now, currently my x value is at 2.3. And if we remember this problem from up above, we wanted to see if there was a value of 6 between 2.5 and 4. So let's think back to that graph again. I said graph. Nope, maybe I didn't. So 2.3, 2.4, 2.5 is right about here. So if I'm looking for the intersection point, I think I want the point over here. So that's important because now we're going to find the intersection. Second calc. And then we're going to go down to intersect, which is 5. Now on intersect, you have left and right options, and you also have up and down options. And you need the up and down if you have more than 2 functions, but I'll show you what happens. Currently, I'm on my pink function, the x squared plus x over x minus 1. If I hit up, it takes me to the green one. Up again is back to pink. If you had lots of functions here, this up and down would take you between all the different functions. We need to tell it which 2 functions we want to use. I'll start with the pink, and for the intersection, I want to move as close to the intersection point as possible. So I'm going to say right about here, 3 point something. Hit enter. Now, when I hit enter, it shows me I'm on my green function. And I'm going left and right here. If you were on the wrong function, you'd hit up or down to get to the right one. and we go as close to the intersection as possible, hit enter again, and it says, should we guess? Again, what it's going to do is it's going to take all the x values close to there, plug them into both functions, and stop when it has an answer that's about the same. And it says they intersect at exactly 3. Okay? Well, is 3 between 2.5 and 4? It certainly is. So we told them that there was one. The calculator did a nice job actually finding it. Now in this guy over here, we didn't know if there was one, but let's go ahead and take a look at the inspire. Okay? If you look, and bonus, if you hover over this, click it down, you can actually drag this out of the way. When I say click it down, I mean you click the little button there until the fist closes. If you look at this, right, do these actually intersect from 1 to 3? No, they don't. But if you wanted to use the intersection tool, it's easy. Menu, Analyze Graph, which is in 6, and then Intersection, which is 4. And what you do is you just take this guy, you click it down once, you drag it to the right, and then as soon as you went over the intersection, it would tell you the answer. But if I click it again, it'll say, error, no intersection. And there isn't one. But that's how you use that intersection guy. We're going to come back to that zero and intersection tool a lot because there's actually kind of 4 accepted uses of your graphing calculator on the AP exam outside of the basic, like doing calculations. And 2 of them are using the intersection tool and using the zero tool. So not only do we know 2 of our 5 theorems, we now know 2 of the 4 functions of our graphing calculator. Okay, so to finish off class today, and you're like, finally, I have 1, 2, 3, 4, 5 questions to go. These ones are all multiple choice questions. And again, if you have time, look at the time. If you have time, then go through and actually solve them. But if you don't, no stress, you can listen to me now. So here we go. We have a function f, and we have a few tabular values. We actually have 3 points here. And I'm actually going to suggest that you graph these points, and I'm going to do it right now. So we're going to graph, ooh, that's not what I wanted. We're going to graph, I see mostly positives there, 0, 1, 1, comma, k. Ooh, the k values are down here. Those are all positives as well. So I think we can probably just stick with the first quadrant for the most part. Okay, and we have 3 points. We have the point 0, comma, 1, 1, comma, k. So I'll just kind of put 1 right here. We'll come back to that. And then we have the point 2, comma, 2, which is over here. All right, now, what are they actually asking us? I'll change colors for this point. Let g of x equal 1/2. We know what g of x equals 1/2 is. That's a graph, isn't it? Y equals 1/2. Right? That's not only a straight line, as most lines are, that's a horizontal line at 1/2. So it's a line that looks something like this. Right? This is the line of y equals 1/2. That's g of x. Which value of k below guarantees that f of x equals g of x has at least 2 solutions? Okay, well, we have 4 k values down below, so why don't we just try a k value of, let's say, 1/2, right? I should do a different color. Let's do a k value of 1/2. Well, that means that I'm going to have the point 1, comma, 1/2, right? So 1, comma, 1/2 puts us right on the line, and that's the most common answer I get on a test. 1, comma, 1/2. Okay? Does that answer the question? Which value of k below guarantees that f of x equals g of x has 2 solutions? Now, when we say 2 functions are equal, we mean they intersect. So they're saying they intersect at least 2 times. Well, we know f is continuous, so eventually I need to get from here to here. But since we've added a 3rd point, I think we're going from here to here. How many times do they intersect? Well, just 1. But think about this. Couldn't this graph go down and then up and then down like that, right? 1, 2, 3. There could be 4 intersections there. But is it guaranteed there's at least 2? No, my counterexample is I can draw this so there's just 1 intersection, and so a k of 1/2 will not work here. So that guy is not my right answer. Can you see the right answer? I bet you guys can see it. I bet you can see that it's k of 0. Right? 1, comma, 0 is down here. And I'll kind of put a little x so we know we're done with that. 1, comma, 0 means we'd start here, we'd get down to 1, 0, and then back up over here. Now I don't know the graph looks exactly like that. It could curve, it could do all sorts of things, but it definitely has to cross 1/2 here, and it has to cross over here. And can you see that if k is 0, that's actually an application of the IVT? Do you see why? Because a k of 0 means that our y values have to cross 1/2 from 1 to 0, and 1/2 again from 0 to 2. It's using the IVT twice because our function's continuous. All right, let's try another. Car travels on a straight track. They give us 60 seconds to look at it, and they told us about the car's velocity. We don't know much about velocity yet. We can think of velocity as speed, how fast it's moving. In feet per second is a continuous function. Gives us selected values of the velocity, right? So 25, we have a velocity of -20. How could we have a negative velocity? Well, it doesn't actually matter, but spoilers, it means you're moving backwards. So they say from 0 to 60, must there be a time when the velocity is -5? Well, as we look at this, v of t being -5, we ask ourselves, could the velocity be -5 between -20 and -30? And it could. It could have dropped from -20 to, like, let's say that this is a time value of 5 right here. What if it dropped to 0 and then went back to -30? That could have happened. But did it have to? Not necessarily. What about here? No, it didn't have to be -5, nor here, nor here. Ooh, what about from -10 to 0? If this is continuous, the IVT tells us that to get from -10 to 0 on this 15-second interval, we had to drop to -9, then -8, -7, -6, -5, hey-oh, -4, -3, -2, -1, until finally we get to 0, right? All the numbers between -10 to 0 had to happen. And so since -5 is on that interval, must there be a time? Yes. But how do we justify it? Well, we write a quick sentence, right? As v of t is continuous on what? Well, they gave us an interval, so let's say 0 to 60. And now we could actually use the endpoints here, because is -5 between -20 and 10? It is. We could use just the endpoints, but I'm going to be a little more specific because why not? So I'm going to take the smaller of these two values here, which is -10, and I'll say that -10 corresponds to v of 35. If you substitute 35 in, you get -10 out. So v of 35 is less than -5, right? That's -10, isn't it? Okay. Which in turn is less than v of 50, right? That's 0. Then the IVT guarantees a time when v of t equals -5. And again, I'm just taking that from the problem. Okay. Let's look at a couple more. The third problem goes faster because it's very, very similar. You're seeing all these tabular problems because I gave you some more equation problems at the beginning. It's good to see tabular data as well. So what's the fewest possible number of times that f of x equals 4? Well, let's look at the f of x values and let's think about when 4 has to occur. If you go from 3 to 4.5, do you have to cross over 4? Certainly. From 4.5 back down to 3, we do, right? 4, 3, okay? From 3 to 2.5, we don't have to get to 4. From 2.5 to 4.4, yeah, we have to cross over 4 again, right? We're just thinking of these continuous y values. So the fewest possible times it has to be 4, well, that's going to be 3. Okay, 2 problems to go. A calculator active one, that's exciting. The IVT applied to f, and that's a crazy function, on the closed interval 10 to 12 guarantees a solution to which of the following equations? So they gave us all these y values and they're like, which one has to happen? Now, there's a few things we'll need to do here. To use the IVT, right, first we have to talk about continuity. Continuity is rough here. However, this only breaks, right, if the natural log is exactly 380. Now that could happen, but I'm actually going to cheat a little bit here. Let's go ahead and just graph this function since it's calculator active, and let's just look at the graph and see if it's continuous from 10 to 12. So what I'd like you to do is to substitute this into your graphing window, hit graph, and let's see what happens. And to do that, I'm going to go ahead and turn off the rest of my graphs here. And we'll see what the calculator is going to do to break everything. So I'll just clear these out so I don't have to worry about them because I'm done with them for now, which is nice. Go away. Goodbye. Goodbye. And let's turn on that equal sign. Good. Graph. Okay. Oh, and my window's weird, so let's do zoom standard. Okay. And then we'll do the same thing on the Inspire, which is going to struggle with me, I'm sure. So we're going to go menu. No, I lied. We're going to go tab. And then I'm going to go up. Turn this one on. Go up. Went all the way up. Exciting. That one's off. I don't care. Good, 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 good. Turn that one off. No, stop. And that one. Good. Okay. We each have those. Great. Move this guy out of the way. This point is pretty irrelevant. I'm going to click on it and hit delete to make it go away. No, I don't want to delete everything. No, I don't want to delete everything. Stop that. Great. Oh yeah, touchscreen is not its friend, but that's okay. There we go. Now, we have an issue because we're trying to look at this graph between an x of 10 and an x of 12. So let's change the window. All right, changing the window is one of my favorite ways to get a better look at the graph. So I'm going to go to Window on the 84, and the minimum x, so we're looking from 10 to 12. Let's go from 9 to 13. That way we're just a little bit outside of that 10 to 12, and then I'll hit Graph. Okay? And then on the Inspire, okay, we'll go to Menu, of course, Window, Window Settings, which is 1, so Menu for 1. And I'm going to go same thing from 9. You can hit Tab to move down, 13, and then just hit Enter instead of going all the way down. But we don't see anything. Any ideas why? Well, hopefully you're like, oh, yeah, I know why. It's because the y values are absolutely massive. Okay, so there's a few things we can do here. Now, one of the nice ways to do this is we can actually use a different zoom on here. And I actually don't like this zoom very much, but it works okay because we set the x values. And the zoom I'm going to suggest we use is zoom fit, which is zoom 0 on the 84. What zoom fit does is it takes the two endpoints, so in this case 9 and 13, finds those y values and sets the window to them. And sometimes it works, sometimes it doesn't. But if I hit enter here, it works pretty darn well, right? And I'll do the same thing on the Inspire. So zoom, which is 4, and then fit, which is A. And we've got our graph. Now looking at that, that looks pretty darn continuous to me. Okay. Now, that's not maybe a great way to do this. We probably should actually set the natural log of x squared plus 1 over 2 equal to 380 and solve, but this is still a pretty good way to go. Especially because if we look back at the equation, they give us 4 y values, and these 4 y values here don't give an option of you can't use the IVT. So I'm pretty sure we can assume that this is continuous. But now let's look at these 4 y values, 0, 27, 42, and 67. What they really want us to do is they want us to find f of 10 and f of 12 and see which of those y values is between them. And that's pretty easy to do. I'll show you in just a second. But now that we actually have the graph, you could actually just trace along this and see which y values are there. In fact, I see 88 up here and kind of 10-ish down there. You might be able to narrow it down. But the other thing we can do is, don't forget, this is f8 of x. It has a name, right? And same thing on my 84, if it lets me go back to it. Maybe not. This is also y sub 8. So why don't I just go back to my main screen, and I'll do the same thing here. I'll hit my calculator button to go back, and let's just find the values of the endpoints. So I'll use the 84 to find the value at 10, and I'll use the Inspire to find the value at 12. Right? So alpha, f4, and I'm going to do y sub 8, which is 8. So I'm going to do y sub 8 of 10. Okay? And then on the Inspire, I'm going to do f8, wherever you are, good, of 12. Don't forget your parentheses. Now, mine's a CAS calculator, so it gave me the exact answer, and it's like, look how helpful I am. I didn't want it to be that helpful, so I'm going to do Control and then Enter to get the approximate value. So we're at 29.544. 29.544, always going 3 decimal places or further. And then f of 12 is 60.207. Starting y value, ending y value. Are any of these y values between those? Well, certainly. It's got to be C, right? That's a y value between those two, and that's it. All right, let's do our last one. It's pretty quick, and then we're done. So here's our function. It's continuous. What's the fewest number of zeros? Well, zeros is when the y value, which is, of course, f of x, is 0. So if you started a y value of 1 and moved to -5, did we have to go past 0? Certainly, 0 is in between those. -5 to 4? No. -4 to 2? Yeah. 2 to -10? Yeah. And then nothing there. So I see 3 zeros. Looking at these answers, there can only be one of them, right? Now, they're kind of complicated on their answer. They said f of 0 is bigger than 1. That's true. And f of 1 is less than 1. That's true. Then they say f of 1 is less than 0. That's true. F of 3 is greater than 0. That's true. Okay. Last but not least, f of 3 is greater than 0. That's true. And f of 5 is less than 0. That's true. So it's a complicated way to justify it, but logically it makes sense. So thank you for tuning in on the IVT, which is actually an easier theorem than you give it credit for. Just is the number between the two endpoints, is the function continuous? But it also lets us explore a whole bunch of nice graphing calculator applications and helps you focus on writing some conclusions. So good luck. We have one lesson left, and then it's time for our first test.